Okay, here's practice exam 1. I just want to kind of go through here and go through some of the answers with you. So on the first page, there are just some graphs of scatter plots, and then ask you to find the correlation for each. Remember that if something has an upward slope, then that means you're going to have a positive correlation, and the closer the points are to the line, the higher the correlation. So these two have positive correlations, and this one's clearly the highest, so that's 0.98, and this one will be 0.58. And then the other two are negative. They have downward slopes, and you want to get the closer it gets to -1, then the stronger the relationship, the closer the points are. And so this one's clearly closer than B, so this one will be -9.5, and this one will be -4.8. And so then you can just go up and this one will be B, -0.95, that was C, 0.88 was A. And I would appreciate on the exam if you would write your answers out in the margin like that. It's just easier for me or my grade or whoever's doing the multiple choice. It's easier for them to grade. Well, anyway, D was then for number 4. And that answers one question. Okay, for the next page, we're matching up histograms to different means and standard deviations. And what I hope you can see in this one, we have means of 8 and 8.5 and 12 and 12.8. So the two on the left here, you can see are centered in the neighborhood of 12 and 12.8. So we just need to look at those two. Those are going to be 7 and 8 and see which one has the smaller or larger standard deviation. And A has a smaller standard deviation as opposed to B. Standard deviation just being how spread out we are. So we're going to get, this one's going to be A, and with the standard deviation of 3.5, that's C. And in the other two, you can see that the center in the 8 or 8-ish range. And again, looking at the spread, this one is B is wide, D is small. So this one will be B, and this one will be D. Okay, in the next slide, we're matching box plots and histograms. And let's see, a few cues here. Pretty easy here that 3 goes with A. You see we have 2 outliers here. That's clearly 2 outliers on there on the lower end. So that's going to be A. And you can see that this is spread out over the way. It looks like there might be outliers, but they're so spread out all over the place that all you're going to get is this long tail here. So anyway, 4 is D. And you can see in a box plot like this one, everything's kind of scrunched in. Almost everything is between Q1 and Q3. And you can see here that a lot of the data skewed on both ends, actually, but everything's right in the middle. So actually, Q1 is going to be pretty close to the bottom, and Q3 pretty close to the bottom. And so 2 is B. And then this box plot C, you can note that there's one outlier there on the upper end, and that's going to be right up here, although it looks like there might be some other ones here. The fence must be right in about here. And you can also see that there's a little bit of skew coming this way, and you can see that this tail on the box plot is a little longer than it is on the bottom. So I guess I should put that down. So on number 13, random sample 100 movies, average length of movie. So the variable is length of movie, and you can measure that in 112 minutes, 108 minutes. You could measure it to be 98.43 minutes. Any reason it's a quantitative variable, and it's continuous. It could be anywhere on the scale. You're not just counting things. So that one's D. 14, random sample 100 moviegoers, 38 buy popcorn from the concession stand. So they either do or they do not buy popcorn from the concession stand. That's qualitative and binomial. Okay, in a random sample of 100 movies, the average length is 114 minutes. The average length of all movies, all, not just the 100, but of all movies, that refers to the overall all population. That is a parameter. In fact, I could have put that it's the population mean. Again, that's from all. If it was just from the sample of 100, this 114 right here is the sample mean, and that would be a statistic, but that's not what the question asked. On 16 and 17, using the empirical rule. If you need to look in the book to see about this, that's in Chapter 3 in the section that talks about 68, 95, 99.7. Just means that the mean plus or minus the one standard deviation includes 68% of the data, or 0.68. Plus or minus, the mean plus or minus 2 standard deviations includes 95, and the mean plus or minus 3 standard deviation, 99.7% of the data. Well, anyway, we have a population mean of 65, and you don't have to draw these out if you can just figure them in your head on the multiple choice, but I will just to explain here. We have a mean of 65 and a standard deviation of 5. And we want to know the proportion of values above 70. So we're looking for out here. And what you should recognize is that this distance from 65 to 70 is one standard deviation. A standard deviation is 5. So that's one standard deviation. Now remember, if we went the mean plus or minus one standard deviation, we would have 68% or 0.68 of the data. But that's if we went the mean plus or minus. In other words, from 60 to 70, one standard deviation on either side. It's a symmetric distribution. So, and we just go in one direction here, we're going to have 0.68 divided by 2, or 0.34 of the data. So from 65 to 70, we have 0.34 of the data, but we're looking for above 70. Well, we know from the mean up has 0.5 of the data. So if 65 up is 0.5 and 65 to 70 is 0.34, then this area in the table here is going to be 0.5 minus 0.34, which is 0.16. So the answer on that's going to be C. Same thing here, we have a mean of 65, standard deviation of 5, and it says between 60 and 80. So we're going to find this area and add those together. 60 to 65, that's one standard deviation. And 65 to 80 is 3 standard deviations. So from 60 to 65, that's one standard deviation. That's 0.34 of the data in there. That's half of 0.68. For 3 standard deviations, here we're going to have 0.997 divided by 2, which is 0.4985. So that's this area. So to get that total area, we're going to add those together, and we're going to get 0.8385, which in this case is none of those. So the answer is E. Okay, so on 18, we still have that mean of 65 and standard deviation of 5. And we want to know where the 97.5th percentile is. That means that 0.975 of the data are below some point x. Well, we already know that from the mean down is 0.5. So that means that the area from 6.5 to x must be 475. That's just 0.975 minus 0.5. Now that 0.475 is, hopefully we'll recognize in this, is 9.5 divided by 2 is 0.475, which that means that we know that this distance right here is 2 standard deviations, or 2 standard deviations above the mean. So we just need to take the mean plus 2 standard deviations, or 65 plus 2 times 5, and that's equal to 75, or F. All right, the next one asks for the 16th percentile. So we're looking for a value such that 0.16 or 16% are below this point. Now the empirical rule tells us the mean plus or minus so many standard deviations. Let me go ahead and put one other thing here. We know from here down is 0.5 of the data. So that means, remember, we can only go from the mean to some point, that this area is 0.34. That's just 0.5 minus 0.16. And that's 0.34 we should recognize is 0.68 divided by 2. So this distance is 1 standard deviation. It's actually minus 1 standard deviation because we're below the mean. So all we have to do is take the mean minus 1 standard deviation, or 65 minus 1 times 5 is equal to 60. Okay, on number 20, it says, suppose you're presenting a paper for a class, and you want to display a graph that depicts the percentage or proportion of customers with, I should say of customers who use various payment methods, such as cash, check, debit card, credit card, when paying for groceries. This isn't part of this problem. Let's recognize that, or I guess it is related, but the type of variable in this case is qualitative. It's what method of payment they use, and it's multinomial because there are 4 different methods: cash, check, debit card, or credit card. So that's multinomial. Well, for qualitative variables, that means we've got pie chart and bar chart. Histograms, relative frequency histograms, and scatter plots all involve quantitative variables. So for a qualitative variable, we're here. And actually, I would accept one of 2 answers for this one. Probably the best thing to use is a pie chart because it's going to divide things up. I know that's not very thing, into 4 groups. And these could be percentages. It looks like that's maybe around 0.3, 0.25, maybe 0.15, and maybe, what would that leave? 50, about 0.3. But it's directly going to show the percentage or proportion in each group. So the best answer is actually A. Now you could use a bar chart where you have the percentage here, and of course, if this were 0.1, 0.2, and 0.3, then you're going to have, using my whatever the things are, 0.3, 0.3, 0.25. There shouldn't be a line right there. Sorry about that. And then 0.15. But anyway, either one of those could use. You could use to show the percentage or proportion. So it could be both A and C. I guess if I had said most appropriate, I would say A. But either one of those will do, although I prefer the pie chart on that. Just can't be any of the following, the ones that are lower than that. But again, I would have accepted on that one A or C, because A and B are both usable for that. But I would actually like it if you recognize that the pie chart would be more appropriate for the display of relative frequencies or percentage or proportion in each group for a qualitative variable. Okay, so the next one says we have an equation for a line that's 12 minus 1.4x, and the coefficient of determination, which is r squared, is 0.81. I may not have gotten this in your class yet, but your book calls it r squared. It is the coefficient of determination. And the square root of that, of course, is r, which is the coefficient of correlation. So we need to take the square root of 0.81, and that's equal to 0.9. There's one other thing you need to pay attention to here. So we know r is, well, that the number part of it is 0.9, but we need to also consider that, and let me say this also, the square root of 0.81 could be 0.9 or minus 0.9. Either one of those squared will be 0.81. So what we want to look at is this a positive or a negative? Remember, it has the same sign as the slope. So the correlation coefficient and the slope have the same sign. And we have minus 1.4 for the slope, so this has to be also negative. So the answer is D. So you have to take the square root of r squared to get r, which is the correlation coefficient, but you also have to realize it can be either sign. In this case, that information you can get from looking at the equation for the line and look at the sign for the slope, which is negative in this case. Okay, so for number 22, just give you a graph of a line and asked you about the y-intercept and the slope of that line. And this is estimating by I. And so what I hope you will remember for slope, or if you did remember before the class, that you think of it now, or I know I've done this lecture in the day sections, but not quite yet in the Monday night class, but you probably remember this anyway, and this in the short run can count as your instruction. Well, anyway, the slope, which is B, is equal to the rise over the run in your graph. So what you need to do is pick two values of x, and I'm going to pick 30 and 40, mainly because they differ by 10. And that's going to be my run. Then I'm going to locate those points on the line, or where they would be, where the x would be, and for 40, about right there. And then I've got a right triangle here. Again, this was the run equal 10. So we need to look at the rise here, and I'm just going to look over and see what y values we've got with both of those. And it's 15 and 10. We went up by 5. That's just 15 minus 10. And so our slope is 0.5. One thing I need to warn you about here, or remind you of, is that if the slope had been going this way, that your rise would have actually been a negative number. It's really I guess you can think of it as fall over run in that case. So if it were this direction and you had the same thing here, it would be minus 0.5 for the slope. But in this one, it's 0.5. We have a rising slope. So the other thing we need, that's the slope, is the y-intercept. And that's just wherever we get where the line crosses the y-axis, and that's at about minus 5. So this is minus 5 and 0.5. That's A. And so we have an intercept of minus 5 and a slope of about 0.5. So on 23, we have data for X and Y. A grade in statistics class is X, and starting salary for your first job after graduating from college is Y. And the correlation coefficient is 0.88, which is pretty high. Remember, the closer to either minus 1 or 1, the higher your correlation. And certainly this is close to 0.9. That's a pretty high correlation coefficient. And so which of the following is true? A, there's a clear association between grade in statistics class and starting salary. That's true. The association, that's what correlation measures, so that's true. You should really study hard for this class because your grade in this class is likely to determine your starting salary. Well, though I'd like for you to study hard for this class, and I hope you do, and I don't want to reject the possibility that your grade in this class will affect your starting salary, but we certainly can't assume that there's a causal relationship. And let me the association does not imply causation. So even though they were associated, to say that the grade in this class is going to determine your starting salary would be maybe a bit of a stretch. So when you see words like determine or cause, you should be very, suspicious, doubtful. I would just say in statistics, saying determine or cause or certainly based on one set of data would be a bit much. So not B. C, a lurking variable such as overall intelligence might be affecting both grade in the class and starting salary for the first job after graduating from college. That's certainly a plausible, an alternative plausible explanation that maybe there is some other variable. That's what a lurking variable is, some other variable that really is affecting both of those. And that's true. So both A and C are true. Your answer should be E. Again, part of the intent of this question, in fact, the main intent of this question, is for you to recognize that association does not imply causation. That doesn't mean that there isn't a causal relationship. We just would be over stating the case if we said that there was. Certainly without other studies that would suggest the same thing. So now we have a set of data here, and we're going to get the 5-number summary, which is just the minimum value, Q1, or the 25th percentile, 1/4 of numbers below this point, 3/4 above the median, 50th percentile, Q3, and the maximum. Well, the smallest value is 8. The largest value is 214. Q1 will be between 25 and 27, and though it really could technically be any number in between there, we're just going to go halfway between there and get 26, and that's what your TI-83 or 4 would do, and many computer programs. Some do it a little bit differently. In fact, what they would do is go 1/4 of the way between 25 and 27. They would get 25.5. But we'll stick with just going 50% of the way in each one. So for the median, we're going to go halfway between 43 and 48, and that's going to be 45.5. And then Q3, halfway between 62 and 70, and that would be 66. That's really all you need for the 5-number summary. Given the space I have on the board here, I'm going to go ahead right here and calculate the IQR, which is the interquartile range, and it's just Q3 minus Q1, which is 66 minus 26, which is 40. And then down here on the bottom, I'm going to go ahead and draw my box plot. First, get me a number line here. That's supposed to be a line. Maybe not as straight as some other lines might be. So the first thing I'm going to do is draw the box. That goes from Q1 to Q3, or from about 26 to 66. And then I'm going to slap the median right in there in the middle. That's at 45.5. That's about right here. And then the minimum value is 8, and I can tell that's not going to be more than 1.5 IQRs away from the box. See the width of the box here, that is IQR, and I would have to go one of those and another half before I got to outliers, and then 3 of those to get to an extreme value. But it does look like there could be some extreme values and or outliers. So I'm going to compute, really doesn't make any difference which way you go. I think I'm going to calculate the fence for an extreme value first. Remember, that's 3 IQRs from the box, and since we're on the upper end, it's going to be from the top of the box, so that's just going to be Q3 plus 3 IQRs, and that's going to be Q3 was 66 plus 3 times IQR. That's going to be 186. That means that the 187 and the 214 are extreme values, and I'm going to go ahead and plot those on here. 214's around there, 187 maybe about there. So now let's see if we have some outliers as well, and an outlier is going to be Q3 plus 1.5 IQRs, or 66 plus 1.5 times 40. That's going to be 126. So the 128 is going to be an outlier, and the 78 is going to be the highest value that is not an outlier and is neither an outlier nor an extreme value. So let's get the outlier first. That's at 128. Designate that with a circle. And then 78 is the last value that's neither an outlier or an extreme value, so we'll extend the whisker on the upper end up to there. Okay, so now we're going to compute mean, standard deviations, covariance, and correlation. So first I'm going to sum. Oh, that wasn't good. I'll try that again. Wasn't expecting that. Okay, so anyway, adding these up, we've got 35, and adding the y's up, we've got 50. And so the mean for the x's is just the sum of the x of i's, the sum of the individual observations of x divided by n, is 35 divided by 5 is equal to 7. And y bar is just the sum of the y sub i's, the values of y we observed, divided by n. 50 divided by 5 is 10. And actually, I'm going to compute the covariance before I compute the standard deviations. And I just find that a little less, a little easier to organize. There's no, you can do it either direction. I really won't be able to tell anyway. But what that's going to require me to do is get the deviations of x from its mean, the deviations of y from its mean. I'm going to leave some space here, and I'm going to get the product or the cross products of those deviations. So for the x's, I'm going to subtract 7 from each value and verify that does calculate to be 0. And for the y's, I'm going to subtract 10 from each value. And that also adds to 0. And then the cross products is just going to be the product of those. So when x goes 5 units below its mean, or when it did go 5 units below its mean, y went 2 below its mean. And when x went 2 units below its mean, y went 2 up. And now I'm just going to multiply here. Let's see here. I get 7 when I add that and do all my adding and subtracting there. And so I'm down here at the bottom here, the covariance, it's a V, between x and y is equal to the sum of those cross products n minus 1. Can't remember exactly, but there is a video on this, at least one on integrity. I think it's maybe around video 8 if you need a little bit more review on this. But anyway, we've got 7 divided by n minus 1. N is 5, so that's 4. So the covariance is 1.75, 7 divided by 4. Okay, to get the standard deviations, I'm going to have to square the deviations there. That's 50. Draw a box around that to make it easier to find in a minute. Y minus y bar squared. I get 34 for that. Circle that just to be able to find it down here. So the standard deviation of the x's is equal to the square root of the sum of the squared deviations divided by n minus 1. And that's equal to the square root of 50 divided by 4. And that is 3.54. And the standard deviation of the y's, same thing except for y sub I minus y bar, the sum of the squared deviations around y divided by n minus 1. The square root of 34 divided by 4, and that is equal to 2.92. So the, I'll go ahead and do this like that. The correlation between x and y then are, if you wanted to put x, y down here, that'd be fine, but that's usually understood. That's just R. Anyway, it's the covariance of x, y, how they move together. And to standardize that, it's a little better, to an index that will be between -1 to 1, we'll divide the covariance by the product of the two standard deviations. And we had 1.75 for that covariance, and we had 3.54 and 2.92. And if you divide or multiply and do your division there, you'll get 0.17. Most people get this, but one thing you need to maybe exercise a little bit of care on is when you put this in your calculator, it would be 1.75 divided by, and then I recommend opening a parentheses do 3.4 times 2.92 and close your parenthesis, and you'll get the 0.17. What some people will do is they'll take 1.75, divide by 3.54, and then they put another division by 2.92, and that'll throw your answer off. The other thing you can do with this, and that I recommend doing, is if you had used your statistical calculator, you could have put the x's and y's. It takes about, I don't know, 15 or 20 seconds. Do stat, edit, and put those in list 1 and list 2. And then you can do stat, arrow over to tests, arrow up to len, reg, t-test, and hit enter. And then if you have your values in list 1 and list 2, and your x list says L1 and L2, you're fine. If not, change your x and y list to match where you put the data. And then just go down and hit calculate. Now you have to arrow down from there. You can see at the very bottom you'll have A, which is the y-intercept. If you arrow down once, you'll get B, the slope. But if you keep going down a little ways, you'll find R, and it's 0.17. And if you had the answer right, then you can feel pretty confident you got this one completely correct if you got down to the correlation. If those don't match up, you might go start seeing where you might have made a mathematical error. Don't spend too much time doing that, or you won't finish the test. But you could also do stat, calc, and then put either in L1 or L2, and find out if you had the means and the standard deviations calculated correctly. Anyway, that's just a way to check your figures when you're taking the test, or when you're otherwise trying to get those. Okay, so number 3, we have a normal distribution, and we have a mean of 214 and a standard deviation for the population of 28.5. And I'll draw that over here. The mean was 214. The standard deviation was 28.5. And we want to know that we're over 250. So remember that whole area under the curve is 1, and using the cumulative table, we can find the z-value here and calculate the probability from there down, from 250 down. Of course, 1 minus that will be the area in the table. So to calculate z, we take the value of x minus the mean divided by the standard deviations, getting the distance right here between 214 and 215, and then dividing that by the standard deviation to get the number of standard deviations from the mean. And that is, by my calculations this morning, 1.26. And then if you will look that up on the cumulative z-table, you should find the number 8962. Again, that's from here down. It's 0.8962. So the area down here is going to be 1 minus that, and that's 0.1038. With that same distribution here, we draw we want to know between 200, which is right here, and 250, which is right here. And so using the cumulative table, what we can do is we can find that area, which, by the way, we already know to be 0.8962. We just did that in Part A. we want to know this area. So if we calculate that area A, which is 0.8962, and then find this area, subtract from the 0.8962, then we'll have what's left in the shaded area there. So for, I'm going to call this B, we're going to have x minus mu over sigma, which is 200 minus 214 over 28.5. And I calculate that to be minus 0.49. Minus 0.49. And it's got to be minus because we're below the mean. And when I looked that up in the cumulative z table, I found 3121. And I'm going to carry that 8962 over here and then subtract. And I got 5841. That's 0.5841 for the final answer there. Okay. Wish I'd left myself a little more space for this part over here, but oh well. Here we go. Anyway, we're looking for the 90th percentile. That means we're looking for a value of x such that 90% of the values are below that point. So we're above the mean. So we're going to be the mean plus z standard deviations, where z is the number of standard deviations away from the mean. So normally we start with a z value and work our way to an area, but now we're using the area, the 0.9, and we're going to back our way into a z value from that. So just go into the cumulative table for the z distribution. Look, we're above the mean, so look on the side with positive numbers, and look in the center until you find a value that's really close to 0.9. I believe the closest you're going to get to 0.9 is 0.8997, and you'll see that's one of the shaded numbers there. So find that 8997, and then work your way out to the z value. You should be in the row 1.28 and the column 0.08. So the z value is 1.28. So this point x is the mean, 214 plus 1.28 standard deviations, which is 28. Well, and calculating that all out, I got 250.48. Okay, the next one, giving an exam to 4 sections of a class, and there's a 10-point bonus question. That's why some people were able to get a score over 100. And so we've got this box plot, or multiple box plot, and we want to know what we can say about the distribution and grades for the 4 sections. And also we want to know which class you would prefer to be in and why. So first of all, let's look at one of the things you can get from the box plot is where the median or the center of the data are at. And so we're looking here, 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 and here. So we can say that class 2 has the highest median. And in fact, not only is it high, the other thing you can do, we're looking at how high this is. I'm going to look at the first quartile here, and I noticed that the first quartile for this one is for class 2. I'm going to put highest median, and I'm going to put Q1 is above the median for class 2 and above Q3 for class 3 and above almost all of the values for class 4. See, there's really only one outlier here above the Q1 for that first class. In fact, that ought to give you the clue right now. Which class do you prefer to be in? The one with the highest grades, of course, assuming that there's 4 sections of the same class. They're all subject to the same curve. So for your sake, I hope you were in the second section. It seems like they outperformed the other sections. Well, anyway, some other things to note about these, the distribution of grades, is that class 1 has the highest spread. It's just more spread out than the other data set and than any of the other ones. See, it's spread all the way from here to here. Looks like there might have been a score really close to about 30 on up to someone who scored a little bit more than 100. And class 4 is the narrowest, so lowest spread, though class 3 isn't that much more spread. It doesn't have that much more spread. So class 3 and 4 are the ones that have lower spreads. The other thing to notice here in class 4 is the presence of an outlier. So from this box plot, you can certainly look at the center of the data. You can look at the spread of the data, comparatively speaking, and then also you can look for the presence of outliers or extreme values in the various classes. You might note that even that extreme value or that outlier in class 4 would only have been the median in class 2. So anyway, bottom line is, in fact, let's look at this even more practically. Everybody in class 2 looks like they passed the exam because the lowest value is around 60. That's not true of everyone in the other classes. Highest average, everyone passes. Some people got over 100. Yeah, hope you were in class 2. We're going to calculate the GPA for a student with the following grades. Remember, the last number in the course number here at Tech is the number of hours. And so if you went 4, 3, 3, 3, 2, and 1, this student's enrolled in 16 hours. So that's the total of hours. And we need to get, well, let's also recognize, hopefully you know, a B is worth 3 points. A C's are worth 2, B with 3, 4 for an A, and 3 for a B. But that doesn't mean you have the equal number of points from each class, because you have to weight it by the hours here. So the points in a class are going to be the product of how many points you get for 1 hour times the number of hours. So 3 times 4 is 12. 2 times 3 is 6. 6, 9, 8, and 3. And that sums up to be 44. And your GPA is just equal to the total points over the number of hours that you're taking, or the total, I guess I'll put it, hours. And that's 44 divided by 16, and that is, if I remember right, a 2.75. But let me check here. That's correct. Okay, the last two problems on here ask you to identify characteristics from the various problems. So in number 6, we've got a random sample of 100 cars. The average fuel efficiency is 21.3. I may have saved this too early. I thought I'd given a different problem on this, but we can do this one. Anyway, the element is one car. We're measuring the fuel efficiency of cars. I think I'll go ahead and say that the population then is all cars. And the sample is the 100 randomly selected cars. And the variable is just miles per gallon. If you put gas mileage or something like that, that'd be fine. And that is a quantitative variable. You can get 23 miles per gallon. You can get 28 miles per gallon. It's quantitative. And you can get 27.3 miles per gallon for one car. That makes it continuous. Possible values would be, as I just said, you could get 28 miles per gallon. A friend of mine once had a car that got 6 miles per gallon. Gas was a little bit cheaper back then. The lowest I saw was, you'll love this, 18 cents a gallon. West Texas, early 70s. But anyway, you could get, I have a friend who gets maybe around 52 miles a gallon in one of those hybrids. But most people probably, well, I'm talking about highway gas mileage here. I guess I should have made that, or at least in my mind, that's what it is. Of course, if you're getting these gas mileages in town too, except for the 52, that actually probably is right in town for the hybrid. But anyway, there you have some possible values that you could get. I suppose you could hope for much higher numbers, and I think there are some cars in the world that maybe they don't meet safety standards in this country, but I think up to maybe 200 miles a gallon now. But if you put 1,000 miles per gallon, I'm thinking you're living in another century. Hopefully we'll get there. Well, anyway, the parameter then, we can see we're talking about means or averages. So for the population, we're talking about the population. Always on the parameter, start with the word population. Then we've got the population mean in this one, and that's symbolized by the Greek letter mu. The statistic then, start with the word sample anytime you ask to identify a statistic, and then we're talking about the sample mean, that's x bar. In fact, we could even give a number on it in this particular problem. It's 21.3. You don't have to do that to answer the question I have here, but that's what it is. Okay, okay, so we have a random sample of 100 customers. 53 return the shopping cart to the corral or into the store. You know, a lot of people just leave them out in the parking lot. Kind of irritates me. But anyway, after they make their purchases, So one element is one customer. So population, all customers. Sample is a random sample of 100 customers. One, sum, all. The variable is whether or not they return the shopping cart. that's enough, but you could go on and be more specific to say whether or not they return the shopping cart to the corral or store after they take their purchases to their cars. Anyway, that's qualitative. You're just putting them in actually to two categories. They either return them or they don't. Of course, then the possible values are yes or no, or you could put return, don't return. Remember, for parameter, we're going to start with the word population. When we have a qualitative variable, all we can do is get the proportion in each category. And that's P, the population proportion. And the statistic is the sample, always sample, proportion. So that's all we can get for a qualitative variable. And that is a P with a hat over it. I'm pretty sure that's all I have on this test. I'll go ahead and tell you that a couple things. First of all, I know now that I'm taking this exam that one thing that I could have put on this practice exam, which didn't, was the stuff about histograms, both frequency and relative frequency, and then frequency distributions. Both frequency and relative frequency on those. So that certainly is something that I could ask on the test. The other thing I'll remind you is that I will include some questions from the test bank that comes with the book. I randomly selected 10 of those multiple choice questions and put them on your on homework too, so that might give you some sense of the kind of questions. Obviously, it's not all-inclusive, but it'll give you some clue. Another thing you could look at is the online quizzes that are on the stats portal. Of course, I think you should read the chapter and watch all of the stat tutor videos on the ebook. So I'll just write that down here, that the stat tutor, I don't know if it had 2 T's or 1 there. I think it had 2. But anyway, you should look at those, and I think you'll be in pretty good shape for the exam. I'd say what I have on this exam, especially included the histograms and that I didn't put on this particular one. So you can go back and watch a video on. It's pretty easy stuff. That's certainly going to, I'm going to say, cover somewhere between 80 and 90%, maybe a little closer to 90%, especially when you realize that even though I'm going to take some things out of the test bank and that those are also things that could have been questions that I asked. So it's not completely independent stuff. I'm not completely doing things different from the text. There certainly should be a lot of overlap. Okay, well, there's